Hello students, welcome to the 36th lecture on particle physics. And in the last lecture, we had started the discussion on cross-section, and what I had told you that cross-section is the probability of interaction or the area over which some A plus B interaction takes place and give rise to one and two particles, say name, I am calling it by name 1 and 2 particles in the final state. And what is important that in the case of neutrinos, the neutrino interaction cross section is very small, and that means probability of interaction of neutrinos with matter is really very small. And in comparison to the probability of interaction, when the interaction is taking place via strong interaction and then via electromagnetic interaction, in the case of weak interaction, is really small. And simply that means that if we talk about an interaction of electron with proton, we know that electron is a lepton. It cannot participate in a strong interaction process, but it can interact with a proton via electromagnetic interaction as well as via weak interaction. In electromagnetic interaction, this will happen when an electron will emit a photon and that will get absorbed by the proton. We'll say that interaction has happened, because in physics, interaction will happen only when there will be a mediating quanta, and quanta for electromagnetic interaction is a photon. While when we talk about the electron interaction with a proton target via weak interaction induced process, then this will happen when a Z0 will get exchanged. When we calculate or we obtain the cross section, the value of the cross section in the case of electromagnetic interaction has been found to be of the order of 10 power minus 30 centimeter square microbarns. And here in the case of weak interaction, it is of the order of 10 power minus 40 centimeter square. And therefore, when we talk about electron-proton scattering, all the time we talk about electromagnetic interaction. Weak interaction is there, but its contribution is really small. Now, let us continue the discussion on neutrino cross-section, or in general cross-section. And what I had told you, that really trillions of neutrinos are coming per unit area, per unit time from the sun, but it's really difficult to detect them. This is because we need either gigantic targets or we need large span of time to detect them, as we cannot change the source of the neutrinos. While in the case of accelerator experiments, which are man-made sources, or even nuclear reactor experiments, if you have got 600 megawatt nuclear reactor, we know that how many anti-neutrinos will get produced. If we have 1000 megawatt reactor, we know that how many anti-neutrinos will be produced. And at many places now around the world, there are 6-8 nuclear power plants which are close by. Similarly, that is true also in India, in Tamil Nadu, where we have many nuclear reactors. And therefore, there you can have huge amount of anti-neutrinos. Similarly, at accelerators, you can have both neutrinos as well as anti-neutrinos in huge amount. But in the case of natural sources, you cannot play with it. Therefore, what you do, you have only two options. Either you build a large detector or you wait for a longer interval of time. Now, the thing which we are talking about, that when we have incident particles and we took the case of loaf of bread and put that into different slices, if you remember, dn was equal to sigma times rho times n dx. This I was telling you that this is the change in number, this is the number, this is the change in number per unit area. This is the number of incident particle per unit area. Therefore, this was per unit area, this was per unit area, this was density per centimeter cube, this is length. Therefore, per centimeter cube, per centimeter square, this centimeter, and here you have per centimeter, number of particles, those are getting unscattered. So therefore, to make this dimension of the same dimension as this, you need here a centimeter square. Therefore, this is 1 by centimeter cube because of rho. Because of n, you have 1 by centimeter square. Then you have centimeter from dx. And then you need to have this dimension of per centimeter square. You need a dimension of centimeter square here. Therefore, the important point, or that the other thing that I told you, that if you talk about dn upon n, then this is sigma times rho times dx. And then this is 1 upon centimeter cube. This is centimeter. Then this you need to be in centimeter square. Therefore, dn upon n, then we said that if the loaf of bread has got a length of L, then we can integrate it from the number. Say here it is Ni, this number is Nf, this is 0 to L. And this is what we are going to talk about here, that the number of particles which have got unscattered will be always less than the number of incident particles, and those, the difference, that means have got scattered. This is what we discussed on the last turn, that Nf is equal to Ni times exponential minus rho times sigma times x. If instead of L, if I am calling the length by x. Now what I had told you, that if you have x to be of infinite length, then that means Nf will be 0, which would imply that all the incident particles those have got scattered from the detector. But you know that this cannot happen. We cannot have a detector of infinite length. But the other thing that I talked about is rho, that water has got a density of 1000 kilogram per meter cube and lead has got density of 12,000 kilogram per meter cube. Therefore, the number of interaction that would take place with a lead target in a centimeter cube will be much larger than in a centimeter cube if you have a water target, because number of particles will be different because of this density. And this will be our topic of the talk in today's lecture. Therefore, what we are talking about, that we have flux. Then what we do in the laboratory experiments, when the target is at rest, we put most of the events, they go in the forward direction, and this we will discuss when we will talk about the kinematics, laboratory frame and center of mass frame in one of the units. There what happens, then we put detector somewhere here and measure the number of events, those are coming in this direction. And if we are measuring the number of events in a particular solid angle bin, which I have represented here by d omega, we say that we are measuring the differential scattering cross section. And when we integrate over all the angles, then we say that this is the total scattering cross section. Therefore, and this d sigma by d omega in literature is also known by the name angular distribution. Similarly, we can have energy distribution, where we say that the number of particles which are coming with an energy between E and E plus dE, say between 10 MeV and 20 MeV, or between 200 MeV and 220 MeV. Then if my detector is competent enough to measure only those particles which are coming between 200 MeV and 220 MeV, then the number of events those we are measuring, we will say that we are actually talking about energy distribution. Now let us take a simple case, and that I have considered it to be water. Water has, as we know, that this is H2O, and H2O means there will be 8, oxygen has 8 protons, 8 neutrons and 8 electrons. 8 protons, 8 neutrons and 8 electrons. while hydrogen has one proton and one electron. We have H2, that means there are two protons and two electrons. Therefore, total number of protons in this water is 10. Total number of neutrons, since oxygen we have, this is 8. Then total mass number is 18. Mind it, here the number of electron would be the same as the number of protons always, and therefore if you recall the basic chemistry, 1 mole of water has 18 grams, and that will be equal to 6, the Avogadro number, molecules of water. 6.023 into 10 power 23 molecules of water that will be contained in 18 gram, and that is what we call by the name 1 mole of water. Therefore, 1 gram, if we talk about, will have 6.023 into 10 power 23 upon 80 into, we are talking about molecules of water. Then in a water molecule, we have 10 proton, 10 electron and 8 neutron. Remember, the density of water is 1 gram per centimeter cube. Now, the density of proton will be then 10 upon 18 into this number, and that will turn out to be 3.3 into 10 power 23 protons per centimeter cube. While density of neutrons, since we have only 8 neutrons, that will be equal to 8 upon 18 into 6.023 into 10 power 23, and that will turn out to be 2.6 into 10 power 23 neutrons per centimeter cube. Now recall the expression for the number of unscattered particles, NF. This is Ni times e power minus sigma rho x. And if what I am telling you, that if we say that neutrino proton scattering cross section is typically 10 power minus 38 centimeter square, then what will be the mean free path for the neutrinos? That means they will go unscattered. That will be 1 upon sigma rho, and this will turn out to be 10 power 14 centimeters. Remember, this is much larger than 1 astronomical unit. And that is why when I was talking about solar neutrinos, I was telling you that sun is rising in United States, but neutrinos are traveling to us via penetrating through the earth, and while coming to us, it has not interacted with the earth's material, or it is not going to interact with us. It will move in the forward direction. That is the important thing, that from here you can just visualize that how difficult a neutrino experiment is, that the mean free path is 10 power 14 centimeters. While if you talk about any strong interaction process where the cross section is 10 power minus 24 centimeter square, then this is roughly of the order of a centimeter. Therefore, you can imagine that the experiments which are being performed in nuclear physics, low energy nuclear physics experiments, where we talk about strong interactions, there the target material is always smaller in size. Grams we talk about, milligrams, macrograms we talk about. But here we are talking about tons and kilotons, because as you can see that we cannot go up to more than this 1 astronomical unit, or we cannot talk about a length or detector's length which is of 1 kilometers, one size of 1 kilometers. They will be always confined somewhere. Therefore, the important point is, now you need to have more neutrinos, or you will have to wait for a longer duration of time, because the event that you talk about, that one event will take place, this will be the sigma times the number of neutrinos those are coming per unit area, per unit time, times the detector that you have. Therefore, the important point is you cannot play with this, because this is the neutrino proton scattering cross section, which will be a fixed number. Neutrino electron scattering cross section for a given energy will be a fixed number. But when you talk about flux, from natural sources, the flux will be fixed. Or even if we have built an accelerator, we know that what's the power of the accelerator, what is its luminosity, and therefore even we cannot play much with the flux, number of neutrinos coming per unit area per unit time, and therefore to have significant event, we try to enhance the size of the detector. We try to have nuclear targets as the detector instead of electron target. Therefore, the neutrino electron cross section is much smaller than neutrino proton cross section, and that is why we talk about neutrino interactions with nuclear targets. That is why we go for water target, argon target, lead target, etc., etc. That is why it's important to understand that in case of weak interaction, we need gigantic detectors, we need large neutrino flux, we need relatively longer time to have or to notice significant number of events. Even if I am telling you that I have got a beam of electrons and tell me that whether there will be any event of electron interacting with a proton through neutral current interaction, then I will say that among 10 power 10 electrons or more than that coming per unit area per unit time, there is a chance of interaction of one electron with the proton target through Z0 exchange, through the neutral current weak interaction process. Otherwise, all the others will be through electromagnetic interaction process. That is why the neutrino experiments are difficult. Now, what I have shown here, that if you have 1 GeV of neutrinos, then the typical cross section is 10 power minus 38 centimeter square. And if you talk about the events, say what I am telling you, the hourly event, in 1 hour how many events, because 1 hour we have 60 minutes and 60 seconds, therefore we have 3600 seconds. The event will be convolution of cross section, flux, time and the detector. As you can see that cross section for neutrino proton scattering is around 10 power minus 38 centimeter square. Flux, say the accelerator which I am talking about is producing 100 neutrinos per centimeter square per second. We want to have 3600 second because we want to hourly count the our data, or we want to take hourly count. And then how much nucleons we are talking about in 1 kilo target material? There will be just the previous prescription. If you look, 1 kiloton means 10 power 3 tons, and that will be equal to 10 power 6 kg, and that will be equal to 10 power 9 grams. Just now, before this, if you notice our last lecture, we have talked about this grams. Just look at it. Yes, you see 1 mole of water is 18 gram, and that has this much molecules of water. From here we have seen that 1 gram of water has this much of proton. So therefore we know that in 1 gram of water we have around this 6 upon 18, you can say this is 1 by 3, and then this 3. Therefore this is roughly 3 into 10 power 23 protons in 1 gram of water. Now we are talking about a detector which is of size 1 kiloton. That means this is 10 power 9 grams. Therefore 10 power 9 grams into 10 power roughly 23, that will be around 10 power 32. This is 6.023 into 10 power 32. Therefore you look at it, you do the algebra, just a simple multiplication, you will find this number to be 2. And you can notice the 100 neutrinos are coming per unit area per second. This is a huge number or huge flux in the case of neutrinos, and then you are noticing only two events. While if I replace this by a electromagnetic interaction process, then this will be 10 power minus 30, and then you will say that there will be 200 million events. Notice, from 200 million events in the case of electromagnetic interaction, now you are talking only about two events, and that is why we go for gigantic detectors to have reasonably good number of events. If we cannot play with the flux, or we don't want to wait for 10 years or 20 years to reach on some certain conclusion, therefore the important point is that events are the convolution of cross section, flux, time, and the detector specification. Specification particularly I am talking about because whether you have lead, whether you have iron, whether you have water, from this you can see that how the algebra is going to change. Now let us talk about, in a few minutes time, the different detectors which are there or which have been used in solar neutrino experiments, in atmospheric neutrino experiments, in accelerator experiments or reactor experiments. And let us start with the solar neutrino detectors. As you can recall, the very first detector that we spoke about worked from 1967 to 1994. This was in Homestake gold mine, and it is in South Dakota, United States. And you can see the interval from 1967 to 1994 to for 27 years, and the target material was chlorine. And what they observed, that the solar neutrinos, the expected from Behkal model and the observed one, there is a big discrepancy, and that discrepancy was of 1/3. Only 1/3 electron type neutrinos were observed, while there was a they were predicted much larger in numbers from the Behkal's standard solar model. Then we had this Kamiokande series of experiments, and then Super Kamiokande series of experiments also. But since these are the older detectors, let us first talk about Kamiokande series of experiments. They had water targets, and here you see they did these experiments in two intervals, and that is why we are talking about Kamiokande 2 that worked between 1986 and 90, and Kamiokande 3 that worked between 1990 to 1995, and then they had Super Kamiokande. When they increased the size of the detector to a huge amount, you see this was 33,000 ton, that means 3 kiloton, and then in Super Kamiokande they had 40 kiloton of target material. Therefore almost 13 times, 12 times more of the target material in Super Kamiokande. Then there was another experiment that is known as Soviet American gallium experiment. Gallium was the target neutron, and then here also you see their findings was that the expected and observed, that is what I am calling it by data upon Monte Carlo. Data, MC here stands for Monte Carlo, and this Monte Carlo was obtained by using Behkal standard solar model. Therefore the denominator is the theory and data is the experimental result, and you can see that all the time there is a big discrepancy, and that is what we call it as solar neutrino anomaly. Then in recent years, we have, in the last 25 years I will say, we have many experiments, and this Super K has many phases, 1, 2, 3, 4, and then they are going to have hyper Kamiokande in the next 4 or 5 years. Therefore, in Japan, these neutrino experiments are going on since the last for more than 40 years, and the important point is that they had again different phases: 96 to 1, 3 to 5, 6 to 8, 8 to the present one, that is super K4. And you see they are talking about 50 kiloton of water target, and the threshold means that these detectors are sensitive to those neutrinos which have energy up to uh, energy more than 4.5 MeV, or more than 0.23 MeV, or more than this 1 MeV, or so on. Therefore, as we have seen that solar neutrinos have a different fluxes coming from beryllium neutrinos, lithium neutrinos, boron neutrinos, pp neutrinos, hep neutrinos, etc. Therefore, these are the threshold of the detector, that detectors are not sensitive to very low energy neutrinos, as you can see from here. And then the plan is the Hyper K experiment in future, Juno in South China, ISNO in Canada. These are the future experiments, and Borexino, Super K, they are the ongoing experiments. While in the last 25 years, you can see that we had Geno, Super K, ISNO, and Borexino. These 4 experiments were running, and then in the next 3 years we expect to have many more. Then we talk about atmospheric neutrino experiments. The atmospheric neutrino experiments were performed to see the neutrinos coming from the pions and kaons, which were getting produced when protons were interacting, the primary cosmic rays were interacting with the Earth's atmosphere. We have dedicated Monte Carlo for that, and that the one that is being used in most of the analysis is by Honda et al. And in the prediction of the atmospheric neutrinos at INO, India-based Neutrino Observatory, or Shalmi Mines, or Sudbury Neutrino Observatory, etc., these have been predicted by Honda et al. For several locations. For a few locations, I have also collaborated with Honda et al. Along with these authors. There are 3-4 authors in this group, including Professor Takaaki Kajita, who is 2015 Nobel Prize winner. Therefore, the experiments which are older, almost 40 to 35 years old, they are Frugis, Irvine, Michigan, Brookhaven Collaboration Group, Kamiokande, Macro, Minos, Nusex, Sudan. As you can see, the experiments are in France, Italy, United States, and Mont Blanc Tunnel, Europe. And what they have found out, that really in most of the experiments like IMB, Kamiokande, and Sudan, they have found discrepancies in the older experiments, while there were also Frugis and Nusex which were consistent with the theoretical prediction. But later, when massive experiments came, like Super Kamiokande and Ice Cube experiment and the others, they found that really there is a discrepancy. And as I have told you, that the 2015 Nobel Prize was awarded to Professor Takaaki Kajita for discovering atmospheric neutrino oscillation at Super K, while at ISNO, Sudbury Neutrino Observatory, McDonald Group had observed, confirmed that really solar neutrinos oscillate when they move from Sun to Earth. And we have discussed this thing in great detail in one of the classes. Now, then we have reactor. Reactor will always produce anti-neutrinos, and we have various anti-neutrino experiments like Shaw, Gosgen, Double Shaw, NEOS, Neutrino 4. And again, you can see that at various places like France, Korea, Russia, etc. And few of them are going on, few of them have taken data, and they have also confirmed that really neutrinos, oscillation of neutrinos take place. Then we have long baseline neutrino detectors for reactors, where they travel to a very long distance, and these are Palovardi, Camland, Dea Bay, Renu, and Juno. These Renu 50 and Juno are the future detectors. Presently, Dea Bay and Camland, they have taken data, and the older experiment is Palovardi in United States. And then we have supernova detectors, as I have told you, that in 1987 it was for this first time observed at IMB and Kamiokande. But the important point is the detectors which are being used for the various purposes, which are sensitive to the dedicated experiments, are also sensitive to the supernova neutrinos, like DUNE, Deep Underground Neutrino Experiment, in United States, Juno in South China, HALO in Canada. Similarly, the older experiments are Mini-Boon, Camland, Icarus, and Large Volume Detector in Gran Sasso, Italy. Therefore, there were many detectors which are sensitive to supernova neutrinos also. As I have told you, that when a supernova burst takes place, then you have all 6 flavors of neutrinos. They are all in equal amount, but their energies are different. And nu E type energy is around, neutrinos of electron type have energies around 10 to 12 MeV, while neutrinos of tau type, they have energy of 16 MeV. But these tau type neutrinos, since they have got only 16 MeV of energy, they cannot have charge current interaction, while electrons can have charge current interaction. And therefore, in the detection, you can charge current as well as neutral current interaction, while for nu mu and nu tau, you can only have neutral current interaction. Then we have short baseline accelerator experiments, where the neutrinos have to travel for a shorter distance, and these experiments are CHARM, Chorus, LSND, Nomad, Carmen, Mini-Boon, Micro-Boon, Icarus, and SBND. Again, you can see that the experiments are spread worldwide: United States, Italy, UK, CERN, European Nuclear Research Center, Geneva, Los Alamos, and the future one is what I'm talking about. Rather, Icarus has started, Icarus in Gran Sasso and SBND. Then there are long baseline experiments where neutrinos have to travel for a longer distance, like 300 kilometers, 700 kilometers, etc. And the different experiments are K2K. This stands for Keck Laboratory in Japan, to Kamiokande, where this Super K experimental setup exists. Then Icarus, Minos, Nova. T2K is again Tokai 2 Kamiokande, Icarus, Dune, and Tokai 2 Hyper K, which is the future plan. Therefore, you have short baseline accelerator experiments, short baseline reactor experiments, long baseline reactor experiments, and long baseline accelerator experiments. But in the case of natural sources, you don't have that choice, because they are coming from either getting produced from the Earth's atmosphere or coming from the sun, or if supernova happens somewhere, they are coming from that place. But for man-made sources, we can have both short baseline experiments as well as long baseline experiments. And these experiments are important to understand neutrino properties, and that will help us to understand matter-antimatter asymmetry, the mass of the universe, weak interaction hadron properties, etc., etc. And therefore, let us stop here. In the next class, we are going to talk about neutrino oscillation. Thank you.